So my name is Bwei, and I'm a graduate student from UC Berkeley. Today, my presentation is about translation and rotation equivariant nominal flow (TRANF) for performing cosmological data analysis. So the central part of statistical inference is the modeling of data likelihood P of x given y, where x is your observed data and y is your model parameters. For the Gaussian case, this likelihood is given by the analytical Gaussian function. If our data is non-Gaussian, we normally do not have such simple analytical expression. So what people do instead is to define some summary statistics and then define your likelihood function on the summary statistics S. The likelihood-free inference does not require you to explicitly write down the likelihood function, but still you need to construct some summary statistics, and it will use some implicit likelihood on the summary statistic S. So you see for this method, for the non-Gaussian data, this method, all of them rely on the choice of summary statistics. And that means you need to compress your data into some low dimensional vector, and that usually means information loss. So in this work, we propose to directly learn the high dimensional likelihood function P of x given y directly with machine learning approach. So here we will not use any summary statistics. We will not do any data compression. So in this process, there is no information loss. And the biggest challenge of this approach is that the data X is usually in a very high dimensional space. In this work, we show that by considering the symmetry of the data, we could actually reduce the model degrees of freedom, and therefore making it possible to model this high dimensional distribution function. So the model we'll be using is a nominal flow. A nominal flow is essentially a bijective map between your observed data X and your and some latent Gaussian random variable Z, which I show on the right. So this transformation F is bijective, is invertible, and is also differentiable, so that you could evaluate the density or the likelihood of your observed data X using this change of variable formula. So it's given by the density of the latent Gaussian random variable times the Jacobian determinant of this transformation. You could also sample using a nominal flow. So the idea is you firstly sample from Gaussian random variable z, and then you use inverse of f to map it to data x. This f is usually parameterized with neural networks, and the key requirements of nominal flow is that this f must be easy to invert, and its Jacobian determinant must be easy to evaluate so that you could efficiently sample and evaluating the density. Finally, after parameterizing the neural network, you could optimize the parameters using by maximizing the log likelihood or log p of your data. And that can be viewed as taking the maximum likelihood estimation of your model parameters. So that's a little background of nominal flow. And now I will introduce our model TRANF, which stands for Translation and Rotation Equivariant Nominal Flow. So we start from convolution neural network, CNN. Since we know CNN already works pretty well for the physical fields, and we know it already has built-in translational symmetry. And now our task is to firstly make the CNN bijective, make it differentiable so that you can put the CNN into a nominal flow framework. And secondly, we want to add rotational symmetry into CNN. So our idea is actually pretty simple. We propose to do the CNN, to do the convolution in the Fourier space. Suppose your convolution kernel is T and your data is X. Then in Fourier space, the convolution can be written as the product between your kernel T and data X. And now we say we need to satisfy the rotational symmetry so that this kernel T, it can only depend on the scalar, the amplitude of the K mode. It cannot depend on the rotation, the angle of the K. So that's the convolution part. And then for the nonlinearity, CNN normally use some fixed activation function like ReLU. Here we try to generalize it to any monotonic differentiable function psi. And so in our model, both the kernel T and activation function psi, they're all 1D functions that we want to learn from the data. And we choose to parameterize them with spline functions. And the spline parameters would be the parameters of this model. So finally, to summarize, the transformation can be of each layer can be written using this red equation, where we take the data X, we further transform it to the Fourier space, multiply it with kernel T, further transform it back, and then apply the activation function psi. So it can be easily verified that this transformation satisfies the translation and rotation symmetry. And also the biggest advantage of doing the convolution in the Fourier space is that we can easily write down its inverse and Jacobian determinant. So finally, we could stack multiple such layer and form a very deep nominal flow model to make it more expressive. So because the TRANF has already guaranteed translational and rotational symmetry, here we do not need any form of data augmentation, and we do not need to ask the model to learn the symmetry. We also have much fewer free parameters because the symmetry reduces the model degrees of freedom. So in a typical setting, we only have about a few hundred or 1,000 free parameters for a 10,000 dimensional problem. So, and remember, this is a generative model, not a discriminative model. So you want to compare this number to, for example, GANs, which usually use millions of free parameters. And finally, the symmetry also leads to faster training and also better generalization properties. Finally, we want to build this TRANF conditional on the physical parameters Y, for example, the cosmological parameters or baronic physics parameters, or even some nuisance parameters. So here we choose to make all the kernel T and the activation function psi, we make them all depend on the conditional variable Y. So in this work, we choose to model this conditional dependence using something called a hypernet. So the idea is we train a neural network that takes in the conditional variable Y and output the node parameters, the spline parameters for all the kernel T and the activation function psi. So finally, the training objective would be the log likelihood of X given Y. And later, I will show that we can use it to get the full posterior distribution without any data compression. So finally, we summarize the architecture of our model here. So here we have our observed data on the left, the latent variable on the right. And here each arrow represents the transformation of one layer. And within each layer, the transformation is defined by the kernel T and activation function psi. And all of them are determined by the conditional variable Y through this neural network. Okay, so that's the basic idea of TRANF. And now I will firstly apply the TRANF to this dark matter over density field at redshift 0. So this data is generated by embodied simulation fast PM, and we choose to vary the cosmological parameters omega m and sigma 8 to, so these two parameters will be our conditional variable Y. For the model, we build a 5-layer of TRANF. So here I list the details of the architectures below, but I won't go into the details. And let's just look at the results. So firstly, we look at the generative samples of TRANF, and we show the samples on the right and the test data on the left. So here, all these samples and data, they are generated conditional on cosmological parameters omega m and sigma 8. So we see that visually they look pretty similar. And also, we can see this cosmological dependence. As we go to larger sigma 8, we see more clustering on the field. We can also look at the samples more quantitatively. So here we show the 1D PDF function, the power spectrum and the bispectrum of our generative samples, and we compare it to the simulation fast PM. And we find that on these summary statistics, they agree pretty well. So the TRANF is supposed to map the data into a perfect Gaussian distribution. So this is what I'm showing in this slide. Here I'm comparing the latent data of TRANF and compare it with the standard Gaussian distribution. So we can see, again, they look very similar. And so I want to remind you that if our model is able to map the data into a perfect Gaussian, that means we have already learned all the information in the data, and the corresponding data analysis would be optimal. So finally, the TRANF give us the full likelihood P of X given Y, so we could use it to constrain the cosmology. So this is, I'm showing this figure where I take 20 test data, and we try to constrain the cosmology using TRANF. So the true cosmology is shown using the black star, and the green contour is from TRANF, and the red one is from the standard power spectrum analysis. So we can see because TRANF actually do no data compression, it can give us much tighter constraints compared to the power spectrum. So in this corner, we show the figure of merit, and we can see the number of TRANF is about 5 times larger than the power spectrum. So you may wonder whether the TRANF have already learned all the information in the data. So for the non-Gaussian data, this is we don't know the true answer, but for Gaussian data, the answer is yes. So here we apply TRANF on the Gaussian random field, and on the left, we show a comparison between the learned likelihood with the true likelihood, and on the right, we show the constraints from the feature information. So you could see that our learned likelihood agrees pretty well with the analytical answer. Finally, if we want to apply this model to the real data analysis, we need to consider several systematics, and they could actually break the data symmetry. For example, we could have survey mask, we could have some position dependent noise, and our strategy here would be to introduce some non-translation and rotation equivariant parts into our model, so that we could model both the physical process with symmetry and this observational effect without the symmetry. So I won't go into the details of this part since we are still working on it, and everything is pretty preliminary. But as a simple experiment, we remove about 50% of the pixels around the boundary to mimic the survey mask, and we show our constraints on the right. You can see it already began to work. So because we remove about half of the pixels, our figure of merit is about half compared to the full images. Yeah. Finally, this is our conclusions. I will just leave it here and take questions.
Questions for Biwei?
The very interesting talk. So I wonder if you have checked the kernel, because you said that there's basically a filter in a Fourier space, right? So have you checked how those kernels are distributed, whether you have like small scale, large scale kernels or combinations of them?
Yeah, we do check the, for example, for the Gaussian data, we do check it because we expect the kernel should be just the power spectrum, and yes, that's true. But for the non-Gaussian data, because we usually have multiple layers, for example, in this experiment we have 5 layers, and yeah, it's hard to actually make physical meanings of them, I think.
Okay. Sorry. One more question is, so the architecture is from one layer to the next. You just choose one kernel, right? And then do the convolution and real space nonlinearity, and then you play it again, and it says finally you just have 5 layers.
Yeah, 5 layers, 5 convolution and 5 activation.
I see. Okay, thank you.
Okay.
Yes, so very impressive work. So did you say that because your latent space now follows a perfect Gaussian distribution, do you expect that that you have really extract all the information?
Yeah, if it's a perfect Gaussian, we learn all the information. Here we can see some very small discrepancy. So I would say there is still room for improvement, and yeah, but overall it agrees with the Gaussian pretty well, I think.
But it's possible that you will follow a perfect distribution, but still you haven't extract all the information, or by construction it has to be like this?
It has to. We have to learn because the Gaussian is an informative. So all the information should be in the Jacobian determinant term.
Thank you.
Questions from the Zoom audience? Okay, I have a question. Do you, it's related to a Seahouse question, not to interpret it, but do you get the same set of kernels every time, or, because it's hard to interpret it, I wonder if multiple sets of kernels can both reduce the same image to white noise?
Yeah, I think, yeah, I have checked, for example, these 5 layers, and they do not look very similar. For example, some of them really focus on the large scale, I think, and some of them are pretty flat, or it's not exactly flat, but have less k-dependence.
I mean, if you initialize them differently, do they always train towards the same answer?
That's a good question. I haven't checked how the result depend on the random seed. Yeah, that's something to check. Yeah, thanks.
So very nice. So I want to ask you. So let me. So you pass your images to CNN, right? First. And after that, you link that to normalizing flow model.
No, we just pass the data to Nominal Flow, and the Nominal Flow itself can be seen as some.
Okay. So then you are flattening all the images, right? Or no?
I flatten?
Yeah. So like the input is 1D dimension or 2D?
No, 2D images.
So then your autoencoder is convolutional. Is like when you compress things like through your autoencoder inside your normalizing flow.
We do not use any autoencoder. It's just Nominal Flow.
Okay.
We use the Nominal Flow to model the whole high dimensional distribution. And there's no.
So which model of normalizing flow you use then? Because there is like the masked autoregressive flow, right?
No,
which has the auto.
Our own method. Yeah, you can see this is the right equation is the flow transformation. It's not the existing Nominal Flow. We just build this from the CNN and by considering the symmetry.
I see. Okay.
Sure.
You ever look at the intermediate outputs? Like, so you have 5 steps. After every layer, you get an output of X, right? Did you ever look at those images to see if there's any visual structure in there? Because like you're going from a Gaussian space to a data space, and what do intermediate, and by any chance do they look anything like you're doing a simulation kind of thing? Like you're getting large scales, constructing large scales first and then small scales or something like that.
Yeah, that's a.
It can be completely meaningless, but it can be meaningful. So I was just curious if you looked at it that way.
Yeah, that's an interesting idea. I haven't actually really checked how it looks in the intermediate layer. I just look at
it. Yeah, I was not asking about neural network weights, just the output after every step.
Yeah, I can check that. Yeah.
The other question I had was like, so all your training parameters are essentially in the conditional neural network, right? Because after the spline outputs, there's no training, like there's no, the T and psi functions.
Yeah, they are completely determined by this neural network.
Right, so all the parameters you're training is in the neural network.
Yes.
Thanks.
Okay, a quick one.
I just wonder, have you checked what about changing the training set, whether you have the same kernel finally obtained, or because finally you just have about 1,100 parameter, right? And you have 5 kernels in Fourier space. So I wonder, what about if you change the training set, whether you find constant, robust, stable result for the kernel?
By changing the training set, you mean changing the random seed?
Yes, another set of relay.
Yeah, actually, I don't think that it really depends on the random seeds, because when we train, we keep checking for example, the loss for the training set and the validation set, and we do not see there's almost no difference between them. So I think it's just because the symmetry actually put very strong constraints on this model. So it generalized pretty well. And
okay. And by the way, I actually have a comment on the symmetry. I think the reason really you can lower the dimensionality is not by symmetry, it's by the function form, the strong constraint on function forms in this normalizing flow, right? Because in principle, you just remove 2 translation degree of freedom and 1 or 2 or 3 rotational degree of freedom by imposing symmetry. So you have a much stronger constraint here, I think.
You mean the architecture of the normalization?
Right. Because you require the kernel to have no angular dependence, that's much stronger, I think, than requiring rotational invariance. That's basically taking the average of all orientations, right?
Yeah.
And we can talk about that later. Sorry.
Okay, let's thank VOA again.
Thank you.
Christina, Colette, Alice, Paco, David, and Shirley. So I'm really interested in kind of like the whole process of how we can add machine learning to different parts of astrophysics. So I think you can kind of break the whole process down. Like, you design an experiment, you observe, you reduce that data, then you maybe convert that data to knowledge. Maybe you upgrade your model, and then you make a new prediction. So I think most kind of like Astro ML, physics ML is kind of at the data reduction step, but I'm really interested in the data to knowledge step, and I think this is kind of like, it's very unsaturated, and I think it would be really good to have more people kind of interested in this area. So the method that I think is very useful for building interpretable models is called symbolic regression. Symbolic regression, it's another machine learning algorithm. So it's supervised regression. You fit a model to predict y, it could be like a scalar, a vector, whatever, given some x inputs. So most machine learning models, you fit like some parameters in some model. In symbolic regression, the basis is analytic equations. So you're trying to search the space of analytic equations to fit some relationship. So you have some data sets, you have some tuples y, x, you try to find f as an analytic equation to match this relationship. So if I have this data, this is my x-axis, this is my y-axis, I basically, when I do symbolic regression, I basically try different symbolic forms. So I say, does this cosine of x? No. Is it sine of x? No. And I keep trying different things. Okay, is it exponent of x? Yes, it's closer. And I kind of use that as my next starting point. And then I try maybe exponent of x over 2. So that's the correct function. So why would we be interested in kind of using equations? So like, so many rules in the natural sciences are accurately described by simple symbolic expressions. So I think really the question should be like, why don't we use this as the space of our models? Like, we know it's such a good basis. Like, why do we go straight to deep learning? Like, we should really exploit this basis. So, okay, so still, like why? So equations are concise. They are very interpretable. You can stare at an equation and immediately see like singularities, like where is it going to fail? What's the scaling in the model? I think probably most important, so we've found this in our research, is like, if you have an analytic equation that simply describes your data set, it tends to generalize much better to out of distribution data than a neural network for physical problems. And this could be like, I don't know, I think this is like a generic statement about kind of parsimony, like simpler models generalize better. And of course, it leads to physical insight because now you have a model that is in the same language as your physical model. So it can lead to new physical insights. So, okay, so how can I do symbolic regression? So if you have like a sum of functional forms, you can use the software called Cindy. So that's more like polynomial searches. If you don't know the functional basis, like maybe you want to search for some nested hierarchical expression, you can use this software called Pyser that I wrote. And it's based on a genetic algorithm. So it lets you search like very flexible expressions. So the way genetic algorithm symbolic regression works is I take my equation and I represent it like a tree. So this is a binary tree that represents this equation. So I put it into this form. Once I have this form, I apply different genetic operators. So maybe I maybe evaluate the equation, and then I randomly do a genetic operator. So I like change the multiplication into a division. Then maybe I change the x1 variable on that leaf into an x2. And maybe I swap out a tree. Maybe I like perturb a constant. So this lets me kind of randomly explore equation space, because you can't take derivatives like of an operator, right? Like you can't take a derivative with respect to a multiplication operator. You kind of have to like use genetic operators to move around this space. So this is the software. It's called the Pyser. You can get it on GitHub. It's a Python package, and yeah, I think it should be. I think symbolic regression should be used more in astrophysics because it gives you like an interpretable basis when you kind of learn a relationship. So this is an example. You give it some operators, you give it a data set, and it spits out the equation at the end. So in general, symbolic regression, it's compact, gives you explicit interpretations, it generalizes well, but it's terrible at high dimensional problems. Like it's complete crap. Like it's so like you have more than 10 features and it's really hard to find a good equation. And this is a fundamental problem of genetic algorithms. They don't scale well with the number of features. On the other hand, deep learning, it's kind of like the complement of this. So very efficient at learning in high dimensional spaces, but it's uninterpretable. You get like linear extrapolation at best. Like maybe you combine it with different symmetries, you get better generalization, but it's really hard to get like strong physical generalization. So the question that I'm really interested in and kind of did a lot of work on last year is like, can we combine the strengths of both and kind of reduce some of the problems with symbolic regression? So this is our method. I'm not going to go into it in too much detail, but the basic principle is you have a deep model, and when you're training your deep model on some problem, you want to sparsify the latent spaces. So inside your neural network, there's different latent spaces, and you try to sparsify those latent spaces. Make them as small as possible, and then you do post-processing on that neural network, and you kind of try to approximate different parts of the neural network with symbolic equation. So you apply symbolic regression, and you can kind of compose those at the end. So basically what you're doing, you train a deep model on some problem, and you try to convert that neural network into an expression using symbolic regression. So if I have a neural network, it's kind of like this hierarchical structure, and maybe I think like that middle space is going to be sparse. What I do is I sparsify that latent space, I fit symbolic regression to the first mapping, symbolic regression to the second mapping, and then I can kind of like stick those together and get an equation. So one thing we're really interested in for like deep learning in astrophysics is deep sets. So if I want to learn some function on like an unordered set of objects, like most of deep learning, like you have images, you use a CNN, sequences an RNN, like a table data, you use an MLP. But there's not a lot of deep learning for like sets of data, right? Like these kind of structured data sets. So this thing called the deep set, and more generally graph neural networks, were introduced. And the basic principle, so this is like a really simple implementation of a graph network. You have a set of data X, you do a mapping from X to some higher dimensional latent space. You do a permutation invariant operation, like a summation in that latent space, and then you have another mapping to kind of map to your the thing you're trying to learn. So this is a simple example of a deep set introduced by this paper, and Battaglia et al. Kind of generalized it into a unifying framework. The reason we like this is it's really good for cosmology because you have these sets of objects like galaxies, halos, voids. So it really kind of suits that data structure. So another way of looking at it like this, if I have this set, so these are my points, I map this to this higher dimensional latent space, and then I do a sum, like a element-wise sum, and then I have a final decoding step. So this is like a normal deep set. So what we propose to do in this paper from this year is, instead of the summation, why don't we do a histogram? So like along every element, you do a separate histogram. So now you have a histogram for like every latent feature. And so we use soft histogram edges so we can kind of learn that mapping. And at the end, we have this histogram for every feature, and then we decode from that kind of n-dimensional histogram. And the reason we want to do this is because, so you can kind of write it like this. The reason we want to do this is you get more information content in a single latent component. So if you're doing just a summation in this high dimensional latent space, you're losing a lot of information by just summing. But if you take a histogram, you preserve a lot of the information because you get a full histogram, right? Much easier to interpret. And there's a lot of functional similarity to summary statistics in cosmology. Like a correlation function is like a histogram. So this is kind of an inductive bias for a deep set that mirrors functions in astrophysics. So if we can interpret the thing we learn, we can kind of feed that back into existing knowledge. So we did like a simple comparison against summation pool, average pool, and so you can see with a single latent feature, we were able to beat it. So this is a void data set. Christina's going to talk about it more tomorrow. You can see with a single latent feature, of course, we beat it because we get more information content in a single latent feature. The advantage of this is then we can interpret that latent feature. So we did this for voids, and it basically tells us like a symbolic form of that feature for voids. And it's a combination of the void radius, density contrast, and ellipticity. And that basically says like this is a good kind of like observable for voids when you're trying to predict omega m. And so this is like learned by the deep set and then the symbolic regression, which is kind of cool that you can interpret it like this. So see Christina's talk tomorrow for more about that. Happy to take questions.
Questions for Miles?
Hey Miles, thanks. Really interesting. Just a small question. Isn't a histogram a sum of indicator functions?
What?
Isn't a histogram a sum of indicator functions?
Indicator functions?
So if I consider a function that takes the indicator that my value is between the two bins of the histogram.
Oh yeah.
And isn't that a histogram just a sum of those things?
Yeah.
Okay.
So like, yeah, like a sum pool and a histogram pool, they're like you can get all the information in a higher dimensional space. The reason you want to take a histogram is because you can do it with a single latent feature and get a lot of information. So it helps a lot when you're in low dimensional spaces.
So then, yeah, I guess that gets my question. What do you mean by the dimensionality of that latent feature? Surely the histogram is like a an n-dimensional object where n is the number of bins. So you say it's one latent feature, but it's really an n-dimensional one-dimensional feature.
Yeah, so when I say one-dimensional feature, I mean like this. You just have like one feature there. You can get a lot more information after the pool. Whereas at the sum pool, you would just sum that, and you end up with a scalar, right? Like it's obviously more information because you can have the number of bins. It's like in the sum pool, it's kind of like you have a single bin, right?
But I can turn my histogram this way, and then it looks just like the features, no? So you look at your histogram bins, you wrote them vertically, but I can turn them horizontally, and then it looks just like your bins, like your features. Essentially, the feature one could be whether that specific instance is in the bin, the first bin. Feature two is whether the specific instance is the second bin, and so on. And then that's like an image transformation between.
Yeah, like again, like the sum pool could compute a histogram. So there's actually some paper by Jesse Taylor's group at MIT where they show. So they learn a deep set on like this particle experiment, and they show that the sum pool is actually computing histograms. So like the sum pool could compute a histogram, but if you explicitly compute a histogram, it's more interpretable. Mm-hmm. That's the basic point.
So in the graph, when you count the number of features, are you counting? So you had this graph where you're counting the number of latent dimensions and plotting the accuracy with respect to that.
Yeah.
Like, shouldn't you be comparing like one histogram latent feature is like
one latent feature here is actually like 100 because you have that many bins.
Right.
Yeah. So like obviously the histogram pool gets more information. That's why we want to do it.
But the dimensioning of the model with one histogram feature is more like the dimensioning of the model with some with like 100.
Yeah.
Right. So you're not comparing models of the same size in this.
Yeah. This is like the number of latent features. And the whole reason we do this is for interpretability. Because we can get like this equation is like for that latent feature. Right? Like that is one latent feature. But if you try to get that interpretation from a sum pool with like 100 features, you would need 100 different equations. It would be much more hard to interpret. Whereas here we just have a single equation. This is the latent feature. If you take it's kind of like the void abundance. Like you take a histogram of this and it's a good summary statistic.
Okay, thanks.
Yeah, go ahead.
So a note and a question. So regarding the generalization of symbolic expressions, there's a limit to that, right? Because you have like, for instance, I don't know, viscous flow versus linear flow and so on and so forth. So different terms have different. So in different regimes, it could be very different.
Also, like different operators, like you choose different operators, and those operators like aren't suited for that domain.
Exactly.
Might generalize worse.
Right.
It's very dependent on the problem, the type of complexity prior.
Exactly. So maybe it would behoove us, let's put it this way, to put different sets of information in different scales so that the symbolic generator could learn different scales and then give us a very accurate description. I don't know. It's just a thought.
One reason we think why in general symbolic expressions have more powerful generalization properties is because of geometry. If you think about polynomials, there's you cube it, it's like volume, there's a lot of geometrical significance to different operators. So when you compress a neural network into an equation, there's a lot more geometrical embeddings
Yeah, I agree. And the other one is a question regarding the efficiency of the genetic operators, right? So there's a recent work done on DAGs, directed cyclical graphs, right, where they basically MC the different structures, right, and then they probe the distribution, get the posterior for what is the most probable DAG that.
The Bayesian scientist paper, which
yeah, I think so.
Yeah, that paper is pretty cool.
Yeah. So maybe there's a way to do that here and to make it more efficient instead of just randomly choosing.
Yeah, it's not random. Like, it's a genetic algorithm. So the algorithm we use is called regularized evolution.
Mm-hmm.
So, like, you're not just brute force searching. You are, every time you do a mutation, you evaluate the model and you decide whether to keep it or not. So it is kind of like MCMC.
Yeah. Okay.
You have like many different like chains. We call them populations, and they run simultaneously, and that helps regularize it basically.
Gotcha.
But I think there's a lot of work to be done. Like, I think genetic algorithms is kind of like the Wild West. Like, there's so many different approaches, and like, yeah, I think there could be a lot smarter things to do here.
Yeah. Good. Thanks.
We have two questions from Zoom. Sam, do you want to ask? Unmute yourself and ask it. So I can read the question. The question is, assuming one wants to have a specific set of features in the final expression, is there a way to enforce that in symbolic regression, which use genetic algorithm as opposed to equation learner, where one can get all these selected features in the final expression?
I mean, like, I think the genetic algorithm, like, it has an internal loss term for the parsimony, like the complexity. So if one of the features doesn't affect the output at all, it won't include that in the expression because it hurts the loss. But I think, like, if you wanted, maybe you could introduce a loss term that punishes the model for not including the feature. But Python doesn't have that.
Okay, thanks. Another question from Luisa. The question is, how robust is the final expression and the values of the coefficients returned by symbolic regression?
So it really depends on the problem, it depends on the algorithm. So my package uses BFGS for finding the parameters. So, like, as good as BFGS determines how good those parameters are. But of course, there's like, it depends on so many other things too. Yeah, like, I think there's a ways to go before symbolic regression is, like, we could call it robust. But the nice thing about symbolic regression is you can interpret it. So you can see the model and you can actually figure out by yourself if it's like, if it makes sense or not. And that's something you can't do with neural networks. Yeah.
Okay. I have a quick comment. I mean, as we discussed earlier, I think it would be nice to have, if you have tensor features, you can contract the indices and to preserve the rotation symmetry and translation symmetry. And so.
So I think, like, in general, for learning high dimensional equations, like, the approach that I keep pushing is you want to put as much work in the neural network as possible. And the neural network will kind of split up the problem into smaller problems. And then you do symbolic regression on each smaller problem. So I think that is, like, maybe a better way to do, like, genetic algorithms are really slow. They're really hard to use. I think it's always best to kind of do the neural network first. If you can model the neural network on the tensor problem, I think that's better. But I think that's definitely interesting too, kind of learning tensor equations.
Thanks. Let's thank Miles again.
I took a red-eye flight over here, and that's like a mistake that I never learned somehow, like, not to make. So I've got a couple of challenges in this slide deck. One is to remember what my, like, deluded self made yesterday last minute for this slide deck. The other is because Sihao made this very good presentation about his work and scattering transforms in general to be a bit complementary to that. So I decided to both zoom out a little bit more and also zoom in a little bit more. Unfortunately, the zooming out part has got to like fit in like 1 or 2 minutes. So here goes the zooming out part, which is just basically scattering transforms applied in many different cases. All right, so here we have audio, where basically that's a 1D time series. You can have wavelets, like different levels of wavelets applied to 1D time series. You can do that with 1D wavelets. On the right, you can do that also on time frequency plots with 2D wavelets, and you can even do that on a pitch spiral to analyze music. Then we move to 2D. So that is arguably kind of the origin of the first applied version of the scattering transform, Joan Bruna's work, where you apply, where wavelets applied to images are analyzed, and it is kind of shown that second order wavelets extract statistics that are basically, you know, beyond the second order moment, and can later on we'll see that it leads to good reconstructions. Laurent Siffre did this with textures and kind of added an equivariance component to that, so you have rotation and translation invariant descriptors. You can add neural networks on top of scattering coefficients, and that typically has been a very good pre-processing. There's a bunch of examples for that. Now we get into more physical work. So you see Howe's plots on the right and at the bottom of reconstructions from scattering coefficients, and that they show some good cosmological constraints. On the top left, you see some fluid dynamic analysis where you also do, where Sishin did reconstructions. Another 2D thing that you can do with wavelets is wavelet phase harmonics, where, oh, this is actually where the fluid dynamics happens. So basically the whole idea here is that you'd like to correlate different scales of wavelet transforms. However, if the wavelets are completely band separated, then you can't linearly correlate them because that'll be 0. So the trick that you do is what you see on the right here. You extract the phase. You extract the phase from the fast-moving thing, which you see at the top, and you extract the phase from the slow-moving thing, which you see at the bottom. And then you accelerate the slow phase, and then you get a correlation again. So that is a way of extracting interesting descriptors, and that has also been applied to cosmology. Also, if you use this kind of idea to train neural networks on ImageNet, you get pretty good performance. Moving on to 3D, a couple of years back, I did some analysis of molecules with kind of harmonic wavelets, and that leads to these very, very molecular orbital-like looking images, but they're fake, but they do you know, they do convey some information about energies and such. And interestingly, very, very recently, this has also been used, exactly those wavelets have also been used for constraining cosmological parameters. So I've got a diagram on the right from that paper. All right, so now we zoom very far in. So what are wavelets? Wavelets are these little squiggles that you see in the second and third row. Second row is a real part of a wavelet. Third row is the imaginary part of a wavelet. And the whole game is to basically analyze images with scaled versions of these objects. What you see at the top is the Fourier transform of that wavelet. The shape and form can be anything. It should sum to 0, and then you're basically good to go. The formula that you have at the top is a scaling formula, and typically we like this kind of logarithmic scaling. At the bottom, you see just the collection of all the, like a wavelet transformed signal. Okay, so the question now is, how do we analyze the Quixote simulations, which are in 3D, with these types of wavelets? So one thing that we can do, well, first we have to think about how do we create these wavelets, and we have a bunch of constraints that are necessary. One is that we need to know exact band limitations in Fourier space so as not to violate, for example, Kmax 0.5 for, in particular, the Quixote simulations. So it's useful to define the wavelets in Fourier space. And in addition, we'd like to have some sort of rotation covariance, equivariance, to be able to create rotation invariant descriptors. And that leads me to wanting to factorize this wavelet into a radial and an angular component. And let's just do that. So let's look at the possible radial component first. Radial component, I'm just going to use that same function that was moving above, which is a little bump that is very differentiable, and it goes to 0 at 0, and it'll just select a part of frequency space. What you see in those 3 rows of the diagram are octave scaling, where the different scales are kind of like double the size or double the frequency of each other. But if that information extracted from those 4 scales is not enough, we can go to half scales or quarter scales and extract all those different all those different scale levels. Okay, now for the angular part. So what do we do once we've got that radial part? Let's look at the angular part. First idea is to oh, interesting. These images weren't supposed to copy themselves like that, but you know, you see an animation here. Basically, this is an angular part that is constantly 1, and we're just scaling up and down the wavelet. Left-hand side, you've got the Fourier space, and on the right-hand side, you've got the signal space, and you see that it like extracts a sort of Laplacian at different scales. So next type of angular constraint that we can add is basically just a function that constrains which angle we're looking at and make a directional wavelet. So you can see when I make that function select only a specific angle, that it becomes an edge detector in signal space. And so we can play around with that. Obviously, I'm showing all of this in 2D, but you can build the same thing in 3D, basically. And the last type of angular function that you can add here is basically harmonics. So this is just a circular harmonic, and in 3D it'd be a spherical harmonic that you can multiply with this angular thing, and then you can also create rotation covariant descriptors. This thing is rotating for no other reason than that I was able to do that in NumPy by multiplying with a phase. So so that's why they're rotating, and you see L equals 1, L equals 2, L equals 3 coming up, and L equals 4. All right, so now for analyzing signals with that. So or let me just summarize this real quick. This is also interestingly shaped. Interesting. Okay. Well, you've seen this. It's just a sort of static summary of what's going on, and it's a little bit bewildering because it wasn't supposed to show up that way. So let me move to how we extract descriptors from any sort of signals. The signal is X. What we first do is convolve it with these wavelets and then take the complex magnitude. If we're dealing with harmonics, we might have to take a sort of complex magnitude over the M space in the YLMs. That's what you see on the right. And then after that convolution, which leaves space intact, we integrate over the whole thing to kill the spatial extent. And we integrate that using different powers. So power 1, power 2 are popular, but we can also go 0.5 and lower. If there is an orientation variable left, for example, for directional wavelets, we want to kind of sample many different directions. Like in Siamak's talk, there were these polyhedra. We typically choose directions along these polyhedra, like an octahedron. And then we sum over all that to get an invariant descriptor. Okay. Now for some numbers that you get when you use these things for parameter constraints. So this is a huge table. Let me draw attention to this red square first, where, okay, first row is power spectrum. So always compare to the first row. You see that all these constraints here are worse than the power spectrum. And I'm including this here because the power 2, if I integrate unoriented wavelets with the power 2, then basically I'm doing nothing other than extract the power spectrum. So it should be worse because I have fewer coefficients. All right. Now I integrate with powers 1 and 2, and I move to the next block. And suddenly the constraints, and let's just like look at the neutrino axis here. From 0.76, the constraint drops by a factor 10. Note that on the other side of this plot, you've got the CB field from which I take the derivatives, and the neutrinos constraints, you know, don't improve that much, but for the total matter field, they do. Then, if I add power spectrum to my wavelet descriptors, I get a slight improvement. But then I can add oriented wavelets, and I get another improvement. And if I add harmonic wavelets, I get another improvement. So the constraints improve with a lot by adding these integral powers, and they improve a little bit more by adding oriented wavelets or like angularly selective ones. I have one of these covariance plots. So on the very right lower diagonal, you can see the power spectrum, and then you can see a bunch of those rows that I just described that are settled firmly within the ellipses of the power spectrum. The upper triangular that you see on the left is basically the new descriptors that I'm proposing here. The outer one is unoriented wavelets that are integrated with powers 1 and 2. And then if I integrate with powers like 1/4 and 1/2 and add some oriented wavelets, I get these tighter constraints that are within. On the right-hand side, we've got the same for the CB field, and there I would draw attention to the degeneracy between sigma 8 and neutrino mass. Okay, we can look at all of this because we have this band constraint. We can look at all of this as a function of K max, and we've got the power spectrum situated pretty high up, and basically all of the wavelet descriptors beat the power spectrum within a very small K already. We can also look at the covariance matrix of these descriptors, and one thing that I would like to point out here is that although they're all very correlated to each other, especially the different powers, there are some things to point out. And I don't have a pointer here. Well, oh, thanks. But that doesn't translate to online very well. But I'll still do this. So basically, we've got power spectrum out there, and then we've got some unoriented descriptors here, and you can see that basically the high and low frequencies become decorrelated, like negatively correlated actually, and that is something that these descriptors add. We can also look at the derivatives of these things, but I've stared so much at this, and I don't know whether that like adds a lot of information. Basically, the derivatives look similar to the ones of power spectrum, but slightly shifted. Okay, so the other challenge that I had was to fit this talk into the robustness thing. So here goes the one slide that actually kind of applies, which is the stability estimate when I estimate the derivatives of the whole the Fisher matrix thing. by subsampling. So instead of using 500 data points, I can use 400, 200, down to 5. And I discover that if I use unoriented wavelets, then and a lot of powers in the third row, my stability basically goes down the drain. But if I add some oriented wavelets, which one can see on the kind of right-hand side, or harmonic wavelets, the descriptors remain stable even when I use lots of integral powers. All right. So the other thing that we can do is apply these wavelet modulus integrals to the camel simulations that Paco talked about this morning. And so there, the setting is basically extract those coefficients and do a regression. And we've got some oriented wavelets here. And what you're seeing here is basically regressing omega matter from 2 different fields, gas mass and total mass. And the sort of 4 plots basically tell you whether you trained on TNG or Simba, or tested on TNG or Simba. And what you can see for the gas mass is if you train and test on the same simulation type, then you get good predictions, but they deteriorate on the off diagonals between the types of simulations. However, for the total mass, you can see that you get pretty good error bars and even cross predictions. And this is just using a linear regression on these descriptors. We can also predict sigma 8, and we basically see a similar dynamic. Doing this from total mass works quite a bit better than doing this from gas mass. And I think this is my last slide. Any questions?
Questions for Michael? Question from the Zoom audience? Yeah.
For the interesting talk, could you go back to the cosmological constraints on the table?
So let me see if I can do this here. Yeah, I've got a back button. You mean the numbers?
Yes. So just a quick question first. What is MK?
Oh, that's the marked power spectrum.
Okay.
So there's the Elena Masara's paper applying the marked power spectrum to these Quixote simulations, which is basically sort of the sort of benchmark for the constraints.
Okay, and could you go to the next slide about the robustness test? Sorry, the next one. Yes. So I wonder why you add more estimators, but it becomes more robust, because kind of intuitively, if you add more estimators, it should be more numerically noisy.
Okay, so there is a subtlety here, which is that, I mean, this whole like numerical derivatives and Gaussian Fisher matrix thing, that very annoying to deal with. So one thing that I did was I kind of preconditioned the matrix. So the Fisher information, especially this Gaussian one, is invariant to linear, basically affine transformations. So I standardized and actually cropped. I standardized it, and I also cropped some features in PCA space to get to a condition number of no more than 10 to the 7. So basically, all of these, have a sort of stable Fisher inverse. However, basically, what the observation here is that I can get very, very good constraints by using completely unoriented wavelets. So they just basically do a sort of scaled Laplacian. If I raise the, if I basically compute the integral by raising the modulus to a power, and if I add lots of powers, especially low ones, then I get very good constraints, but it is to the detriment of the stability. So that's what you see in the bottom left here. Basically, you've got powers 1/8 all the way to 4, and in that case, you see that basically this thing doesn't remain constant. Then, if I add features, oriented features or harmonic features, basically the procedure, like the constraints, basically have better things to work with. So it's like they don't need to use those powers that that cause the constraints to go bad, and they can use, you know, orientation information or harmonic information, and potentially my conditioning crop throws a bunch of stuff out that that leads to bad stability. So I think that's what's going on.
Okay, thanks.
Okay, in the interest of time, let's thank the speaker again.
So I'm going to talk today a little bit about Tyler's talk is compromise-free, likelihood-free inference, and Bayesian neural networks, which kind of combining two things here, really. And I'll explain a little bit what I mean by compromise-free, is that's kind of the tagline, I suppose, for what we're proposing here. It's a bit of a difficult thing in the machine learning space to come up with good naming for everything. It's quite a crowded space, I think, in that respect. And I'll talk a bit about Bayesian neural networks as well. So I'll go to my first slide proper. I've given the game away a little bit here with this picture on the right. So actually this would have been my first cosmology conference or astrophysics and any of that kind of thing. I'm actually a particle physicist by training. So I was at CERN and doing all of these sorts of particle collision stuff, which is another branch of, I think, you know, there's a lot of interesting crosstalk, and I think interesting crosstalk going on at the Flatiron Institute, and all sort of people involved across both fields. And there's definitely some interesting stuff to learn between these. And what I wanted to state in this slide really is that, you know, I think we've seen lots of different people sharing different ideas they've been looking at, and it's quite a broad fields that we're talking about here, or broad church, as I've called it. And what do I mean when I talk about this? Just to sort of set my stall out correctly, in a very sort of high level, broad strokes idea is you have something where the likelihood is intractable. So to me, that means these sorts of particle collisions, but I'm sure there's all sorts of fascinating n-body simulations going on that people have been talking about. And then what I want to do is I want to define some kind of surrogate likelihood that I can then fit to this simulation data. And this has a number of advantages, and I think there's been lots of recent developments in partly how we define these surrogate likelihoods, so lots of things to do with neural networks, and lots of different structures and architectures that people have been looking at, as well as a growing need for this sort of technique from bigger data and all of that sort of thing. So by compromise-free likelihood-free inference, then what do I mean by that? Well, the idea is that we're going to use state-of-the-art likelihood-based techniques, and by that I mean nested sampling on this surrogate likelihood, and see what we can do with that as a sort of broad idea. This is somewhere where my lack of experience as a cosmologist shows, because certainly in particle physics, if I was to come in and mention nested sampling, everyone would look at me in a very confused way. I understand this is something a bit more endemic in the field here, but it's perhaps maybe still a bit specialist, but it's essentially some kind of Markov chain style approach that will let me do integration, and I'll talk a little bit more about that as I go along. The other aspect I wanted to talk about was Bayesian neural networks, and this is another thing, I call it a big tent. I think that's a phrase from UK political discourse, so I've stolen that. But it's another thing where I think lots of people are coming at this from different angles, and lots of people have different requirements that sort of circle around this as a topic. Fundamentally, it's really just a different training paradigm in a lot of ways. It's not really a structurally different thing that you're talking about. You're talking about sampling across your machine learning architecture rather than doing it purely by an optimized approach. So at its core, we still have these sort of neural network techniques, which are going to be, as we've seen everyone talk about, it's very endemic in likelihood-free inference. The second point that I think, again, is something people sort of bring up quite a bit, is that, we're talking about precision science, we're talking about our particle physics, we're talking about our cosmology. Precise statements about uncertainties are important for us to make. And this is something that is, is traditionally well known to be a difficult thing to do with maybe maximum likelihood style optimization of neural networks. And this is something that Bayesian inference can obviously give us a bit of a window into. And like I say, there's a few, if you look up what a Bayesian neural network is, there'll be a bunch of different ideas out there which have all got varying sort of approximations in, and of course what we're doing has some kind of approximation in as well. So you often see people talk about things like training with dropout or variational inference, and these all have different sort of degrees of robustness, you'd call it, in a sort of Bayesian sense, I suppose. So when we're talking about doing nested sampling in this we're talking about doing a sort of fully numerical posterior sampling across my architecture here. And one of the really nice things that we will have access to when we do this is this sort of 9 different architectures here that are quite, they're quite small. This is still sort of toy stuff we're talking about. Typically what I might do is I might view this as a hyperparameter optimization, and I might pick the one that suits best the problem I'm working on by individually examining these things. If we can perform this sort of fully Bayesian marginal likelihood evidence calculation across all of this and have my architecture choices as discrete parameters, then I can incorporate the Bayesian evidence into as an alternative to my hyperparameter optimization. So there's a few things in that I think are quite interesting and have some mileage. A little bit more on that then, so just some sort of details and some references. What I'm talking about today is a continuation of some work that I put here, which is where I got this phrase compromise-free from. It depends how you want to differentiate yourself, I suppose, from other Bayesian neural network approaches, and that's what was chosen. And what we're doing here is nested sampling for neural networks, and it's done using polychord, for which the reference is here. And that's really the perspective I'm coming from. Is I've joined the cosmology group at Cambridge, which develops a lot of this kind of software, and I've joined the group there, and we're trying this out more as a machine learning problem. And I know very little about cosmology, so it's an interesting thing for me to try and learn. But it's also interesting for me to develop these sorts of techniques. And we're doing this here. There's full posterior sampling, which I'll demonstrate in a second. And we're trying to, whilst you're doing this posterior sampling, which you could of course do with something like Hamiltonian Monte Carlo, you're also keeping track of your evidence integral, your marginal likelihood integral, which is what's going to let you make these kinds of evidence-based choices. You of course have to be pragmatic, and you have to be honest about what you're doing here. So I put a little disclaimer at the bottom, is that of course I think the obvious question people will ask with this is, what size network can you do? And I can go into a bit more detail about that. But you are going to trade some of the dimensionality of your surrogate model that you're able to train for a more precise understanding of the architecture of that surrogate. So it's not going to be a paradigm that it works in every single application, but it's really targeting some more detailed understanding of when that is required. So one more note on this then, I had to choose an example from HEP, so I apologize, or high energy physics, or particle physics, MadMiner here, which is a reference to this. It's just a likelihood-free inference framework that people have been built. I think actually some people from NYU certainly were involved with this. And the reason I want to just bring this up is just to kind of contextualize this a little bit, is when you do something like this kind of inference problem, this sort of likelihood-free inference problem, you're not talking about doing something like ImageNet, right? So a lot of the sort of received wisdom that you get on what is and what is not numerically feasible is built from these ideas of doing these very general purpose architectures, which have millions and millions of parameters. This isn't really what I'm trying to do here, and it's not really what I want to do as well in precision science. So I'm doing something a bit more compact, And the thing that I wanted to, part of the reason for coming here and sort of chatting about this in this context of likelihood-free inference is this something that, you know, the dimensionality of the problem might match up quite well with the sort of things that we're looking at doing as well. And another note, I think, is that, you know, this dense, fully connected, quite simplistic neural network, these are often the brute force, I suppose, and you could actually come up with more refined suggestions for what your architecture should be that might be a bit more efficient in terms of how they share the information around within the network. So things like convolutions are more efficient than just doing dense sampling for the whole thing. So the idea is that hopefully the complexity required to do sort of likelihood-free inference with the sort of Bayesian neural networks that I'm talking about might be in reach of sort of meeting up. Okay, so it's still quite an early prototype, but I'll just sort of demonstrate a little bit sort of what it looks like on a very simple problem. So this is just completely a toy problem, no data at all, about as simple as can be. You don't even need a neural network to do this, right? This is a very simple problem where I just generate seven points that I sort of choose randomly, and then I can just generate some classification data randomly around those points. So red versus blue, just a binary classifier. So this is a very, very simple thing. And you can solve this very easily with quite simple network architectures. But that's good because we want to try and understand what we're doing with this. So if I run this kind of paradigm of sampling across my network to do this, this is the sort of output that you can sort of start to get, which is quite nice because you're already getting you know, the sort of features of a Bayesian calculation that you want, where you have a full ensemble of network weights that you can sample from. So you do have a sort of full inference for your classification problem itself. And that's just a little cartoon sort of this. But perhaps more interestingly is what this looks like. So this was just this was just done with a sort of four nodes. So it's really not that not a big network at all. But one of the reasons why this is an interesting problem, one of the reasons why it's quite tricky, is that neural networks are actually they're quite picky to work with, and they can actually be quite multimodal. They can have a lot of degeneracies within them, and that makes this problem very hard. But it also exposes some of the motivation for doing this in the first place. So this is, if you were to approach this kind of problem with a typical optimization, you might pick one of these orange blobs where this sort of represents 3 different modes that seem to give about the same solution. But you might be missing some of the information that you're actually getting whilst you're solving this. So that's just a little sort of cartoon of what it looks like, just to contextualize it. It's still kind of early work, so it's still sort of being pitched. This is still a sort of work in progress. But I'll just sort of wrap that up and conclude it then. So the thing that we want to look at and the thing we wanted to start talking about is really proposing this as a kind of full sampling paradigm for neural networks. You don't have to sample the whole thing. You can optimize portions of this and sample different portions of it as well. And it's interesting to see what extra information that tells us about our problem, and that's what we'd like to kind of try and see if that has good applications on actual data in cosmological problems. So we're talking about integrating over entire networks, calculating Bayesian evidence of our surrogate networks, and all of that sort of thing. Again, I sort of mentioned that likelihood-free inference scenarios sort of intersect with the sort of complexity that we think we're able to achieve with this. So this is hopefully a good fit. And it'd just be interesting to chat about that further. So hopefully there's some discussion in some of the offline, less organized sessions. But thanks for listening, and thanks for putting up my technical problems.
Thanks, David. Questions? From the Zoom audience?
We have a question on Zoom.
Oui? Can you hear me, David? Oh, someone. Francois.
David, can you hear me?
It's quite quiet. Yes.
Okay. So my question is how interpretable and how useful is the full posterior that you're hoping to achieve? So I think what you're doing is really, really interesting. But my usual question with Bayesian neural networks is how useful is that posterior, given that we don't really understand what prior we are putting on the model?
Yeah, so I think this is something that is it is an interesting interesting problem for this. It's how much value do I put on understanding my surrogate likelihood to these sorts of details as well, right? It is something where if I'm doing a MCMC sampling of my my explicit theoretically derived model, I want to understand how all of these parameters interact very well. It might not be something that's particularly useful in the internal architecture of this. I think that's one of the reasons why trying to do sort of Markov chain style sampling of these sorts of things to just derive the network posterior is maybe not actually the most interesting part of what we're trying to do here. I think the most interesting part is actually calculating the marginal likelihood of these things. So this is, I think it has a really nice property of being your hyperparameter optimization, but doing it in a way that I think is defendable. Certainly something that I found in high energy physics is you'll often get quite a bit of opposition to, if you were to present, let's say, in our paper, we looked at these architectures and we picked this one because it gave me the best loss and the best, the best cross-validation metrics and all of that kind of thing. A lot of more traditional scientists might be a bit, a bit off-put by that, as claiming you're sort of cherry picking what you want. So one of the nice things about this, I think, is really this idea of doing this hyperparameter scan in a kind of principled sense. But I do agree, it's not entirely clear to me, how useful is knowing precisely how good precisely the posterior of my network. If given it's just some arbitrary function I fitted, it's not always immediately obvious. That's the key selling point.
Any other question? I have a quick question. So before cosmology was, before cosmologists apply having statistics in their studies, so particle physicists started to use statistics much earlier. I think the same was true for machine learning, kind of. So is there any tool for particle physicists, machine learning practitioners that you think it's very valuable for cosmologists?
Yeah, I think it is one thing that's, I think the sociology of some of this is actually quite fascinating because in particle physics, for those who are less familiar, it's very entrenched frequentist statistics. So there's almost no usage of Bayesian statistics at all. Which is why I'm a bit of an anomaly coming over to work on almost exclusively Bayesian analysis software. So I think that's encouraged a lot of, because that also fits in quite well with the current, leading machine learning paradigm is really based on lots of parameters, fast optimization, essentially maximum likelihood techniques, which fall under these kind of frequentist banners. So I think it sort of maybe fitted a bit more naturally with particle physics. And maybe given that cosmology, at least to me as a sort of someone coming into the field, seemed to have quite a strong traditional focus on Markov chain analyses, it's actually kind of a different way of thinking about it. As for kind of specifics, I think it's something that you kind of need to sit down and work on, or figure out what the problem is, and then work out what the analog would be in terms of my, the way I think about everything is a bit unfortunately tied to this picture. So in some ways it's an exercise in sort of translating, given what I know about this, how would I translate that, given that there's often similar challenges. So I think it'd be a bit more problem specific, but there's certainly a lot of things that have been developed in particle physics that are quite interesting, I think, and it's something I'm trying to learn about in cosmology anyway.
Thanks a lot. Okay, let's thank David again.